Hi there, and welcome back to Math of Finance. So our end game here with what's left of the semester is to try to look at some financial calculations, and particularly when interest is building up over time. The catch is, in order to do that, we kind of need to put a few more tools in the toolbox over what we've been working with previously. So if you've got that notes handout that I have posted in Moodle about section 5.1, exponential functions, great. If not, I'm kind of taking for granted that you have it at your disposal, whether it's a printout or just the PDF sitting alongside this video, whichever's fine. So the idea here is an exponential function looks like this. So a is technically some fixed number. It's a positive number. We don't let it equal 1. Those are the only real constraints here, but it is set in stone. The variable in this instance is sitting up here in the exponent. That's why we call it an exponential. So that is a bit of a difference from the types of things that we've seen before when we were talking about, say, quadratic functions, where the variable was down here in what we call the base of the exponential expression, and then we had a fixed exponent. We were always squaring or always raising it to the third power or something like that. So that does fundamentally alter the way these things behave, where that variable happens to be versus where a locked-in number is living. So that's kind of the setup right here. Exponential functions can be broken broadly into two main classes. We'll talk about them momentarily, sketch out their basics, and look at some examples of them in action. So the first guy we're going to talk about is what we call an exponential growth function. So that's the type of thing that's happening when interest is building up in an account over time. So if things are growing. So the general formula in that instance is going to look like this. So we have some constant a. By design, we assume that that constant c is something positive if we're talking about exponential growth. Hopefully that makes sense. And we're going to assume for exponential growth that that value a, what you might call the base of this exponential expression, is in fact greater than 1. So we have like 2 to the x or 5 to the x or something along those lines. So that's kind of baked into the assumptions if we're talking about exponential growth. So there are, some baked-in things that, again, happen for all exponential growth functions. So as it turns out, the y-intercept, as hopefully you'll recall, occurs when you let the variable x equal 0. If you feed x equals 0 into this thing, raising positive numbers to the 0th power gives you a 1 back, so you have c times 1. Thus, your y-intercept as a coordinate pair looks like 0, c. So the domain of our function, which you may recall from way back in chapter 1, is the set of x values that we can meaningfully feed into this thing. As it turns out, our domain is still all real numbers. There's no x value we couldn't meaningfully plug into this. Nothing weird is going to happen as a result. So the range is the set of possible y values that this thing is going to end up hitting at some point, depending on the various values of x you try to feed in. As it turns out, the results, the outputs, if you will, are always going to be positive. Y is going to have to be greater than 0 in all instances. I'm going to post a separate video where we actually take a look at some of the graphical behavior. So look for that, to sort of give you some guidance as to what these things look like graphically. So that's an exponential growth function. So I wanted to take a look at one of the examples in the notes handout where we've got something in terms of an investment account. So if you take a look at the example, it's listed as exercise 32 on the sheet. We have $1,000 invested for X number of years, and we're compounding interest basically the instant it builds up. We'll talk more about what that means when we get to chapter 6. For now, just roll with it. We give you a formula there. Now the catch is that formula, it mentions this thing that there's an e sitting in it, if you notice. And e is kind of an odd thing you might not be used to thinking of. You might go, well, there's another variable. What exactly does that mean? E is not a variable in this instance. E is in fact a fixed number. The catch is it's not a number that you can describe really elegantly, in a sort of a fixed integer format. It's not 10, it's not 7 or anything like that. The notes handout suggests that E is approximately 2.718. You can actually get a little more precise. So as it turns out, if you want to be really, highfalutin on this, you're going to have that as a pretty reasonable approximation of E for just about anything we're going to need to do in this course. That's, that's the setup. So now that you've got that guy there, now we have what looks like one of those exponential growth functions, a constant 1,000 times E, a base raised to something. It's technically got a coefficient in there if you look at the formula. We'll see what it looks like in a moment. But you've got this guy in here. So we have 1,000 E to the 0.10, so times x. So the 0.10 and the x are both in the exponent in this instance. So that's our setup, and we want to know how much money we would have sitting in this account after 5 years. So the idea is we're going to be plugging in 5 for x into this thing. So that's our setup. So it's going to look like that if we feed it in. Now you need to be a little bit careful in terms of calculator software, how you go about entering something like this in. So we've got 1,000 E. Both of these guys live up in the exponent. If you're not careful with your order of operations, it can kind of mess up and not put you in the right place. The way I would type this thing into my calculator would look like this. So I have 1,000. I hit my multiplication key. The calculator is actually going to have a built-in E to a particular power setup, so I've done that. Some calculators will automatically enter some parentheses there. If yours doesn't, go ahead and put one in. So that's what the setup is going to look like, 1,000 times E to the 0.10 times 5. And again, if it turns out you're having a hard time with this, I'd recommend going ahead and doing this multiplication first and then using the result in 1,000 times E to the stuff. So if you work all of that out, this is a dollar figure, so I'll put that there. I got $1,648, and if we go to the nearest cent, 72 cents. Okay. So that's an exponential growth function in action. Another example uses this exact same formula and then asks you to see what happens a few more years down the line. That's something I'm leaving for you to work on. Now, moving on from what we just did here, I said exponential functions can be broken into 2 broad classes. We've talked about exponential growth. The other option is what you might call exponential decay functions. So that's the sort of thing where you might need to be concerned about in terms of the context of this course, where you have money locked into an account and it's basically losing value over time because inflation is a thing. So decay functions look pretty similar in format. So you could have CA to the X. The catch is, if you set it up this way, the A value is a little bit different. C is still some positive constant. A, however, now would be something that lives between 0 and 1, like 1/2, or there's an example in the notes file with 2/3. We'll take a look, again, we'll take a look at the graphs of these things momentarily. On the other hand, you could interpret this a little bit differently, where you have a negative exponent. So we haven't talked a lot about properties of exponents, but yeah, that kind of takes care of this, and then it lets us continue to use like a value of a greater than 1. If you like sticking with that consistently. It's kind of 6 of one, half a dozen of the other, but that's our general format. As it turns out, those other graphical qualities that I talked about, the domain, the range, and the y-intercept, they're all the same as they were for the exponential growth function. So I'm not going to reinvent the wheel here. You can graph those from before. They pop up the exact same way. So we're going to take a look at some of the graphical stuff, as I said in another video, but I did want to investigate an example before we call it a session here, where we look at purchasing power. That was, again, sort of the example that ends up getting presented in the notes file. It still ends up using that number E, but the idea is if you had $30,000 and it starts losing value against inflation over time, you're going to be looking at something. Say the variable there, it says is t instead of x. My apologies, I'll do my best to make my t's not look like plus signs. So the idea is, we started with $30,000. If we let it sit there, the idea is, what can it buy us a certain number of years down the line? That's what t is representing. So if it turns out t is 5, so e to the negative 0.04 times 5 again. Once again, in terms of calculator format, this would look like that guy right there. So we have the 30,000 times E, hit that. So negative 0.04. Again, keep in mind that should be the negative key, not the subtraction key, just in case. Most calculators separate them into two separate functions. So put multiplication by 5. Again, if you're struggling with getting this formatted appropriately, feel free to work out the multiplication yourself. And the purchasing power that I came up with after that was, double checking and making sure that I can read my own handwriting here, we have $24,561.92. So in just 5 years, our account's already lost over $5,000 worth of purchasing power. Yay, inflation. So that's a quick introduction to how to work out exponential growth and decay functions. Again, look for the next video where I'm going to show you what these things look like from a graphical standpoint. So stay tuned.